So what makes something organic? That is actually a much harder definition than we actually really care to go into, so we're not going to stress too much on it. Minimally, you will see carbon and hydrogen in a combustion reaction. Okay, you may see other elements show up in there. As far as predicting this type of equation, really all you'll see would be carbon and hydrogen. You might see oxygen show up, but you won't see any other elements. And the idea is that you react that organic material with oxygen gas, and it produces CO2 and water. So a relatively straightforward process. So if we think about gasoline in our cars, we're doing a combustion reaction. Theoretically, the only things produced would be CO2 and water. Okay, but we get a bunch of other nasty stuff coming out of it. Why do we get a bunch of other nasty stuff coming out of it? It's not pure hydrocarbons. Okay, so there is other chemicals found within that. One way to kind of evaluate that is you notice they have, what is it, 85, 87, 91 on ranking those premiums. What are those numbers in reference to? It's the purity of gasoline. Okay. So it's 85% pure gasoline versus 87 versus 91. So the more pure it is, the cleaner it'll burn, and the more efficient your burning process. So that's why premium, it goes up higher and higher because they purified it more. That's why it's more expensive. So where this can come in be a problem is when you go through to try and balance these types of questions. Okay, so let's take a look at an example here. We've got C4H10 plus oxygen. And you'll notice the oxygen is O2. Why not just O? It's a diatomic element, so anytime we see oxygen by itself, we should be assuming it is diatomic. The one case where it would not be is if it is directly referenced as an oxygen atom. If you don't see oxygen atom, particularly that word atom after it, you should be assuming diatomic. This goes through to produce carbon dioxide and water. Okay, so instead of me helping you balance this right out of the gate, I'm going to have you try and go through and balance it. And theoretically, you will encounter kind of a hiccup partway through it. It's that hiccup that we really want to talk about. Okay? So use your balancing rules. Identify the elements that show up the same on both sides, and make sure they balance out through the equation. As some hints, we can start with carbon, move to hydrogen, and we can move to oxygen. So take a couple. So remember, when balancing, what we can do is specify our elements right through the middle, underneath that reaction arrow. Okay? And what we'll do is look to the left side of that reaction arrow, and those would be our reactants. How many carbons do we have on the reactant side? Okay? According to our formula, we have 4. So we can write a 4 next to our C underneath. Okay? What we are trying to do is have a paper trail, if you will, of the work that you've done. If you do this internally, unfortunately, this is a case where you will probably fail, okay? Because you have to go back and do a whole bunch of extra work behind it. Okay? On the right-hand side of the equation, how many carbons do you have? You only have 1. So what we need to do is to make sure that there are now 4 carbons on the right-hand side. How do we do that? We change the coefficient to a 4. We do not change the subscripts. Why not? Then it's not carbon dioxide. You've changed the molecule. So we cannot change our formulas once we've started balancing the equation. We now have 4 carbons. Okay. Next thing that I'll mention, which I should have mentioned just a little bit earlier, was I noticed a lot of people went through and just said, okay, how many carbons do I have on the right side? How many carbons on the left side? How many hydrogens do I have on the left side? How many hydrogens on the right side? How many oxygens? How many oxygens? And then you went through and tried to balance. Okay. Well, the issue with that is that as you then go through and balance, what happens to the number of atoms? It changes. So all that work you went through to do and total how much you had on both sides of the equation before you started balancing is now wrong. So start with carbon. Once carbon is balanced, then move to hydrogen. Once hydrogen is balanced, then move to oxygen. Don't start counting prematurely because it's going to change. Okay, 1 at a time. Hydrogen. How many hydrogens on the left side of the equation? How many hydrogens on the right side of the equation? 2. How do I make that 2 into a 10?
5, because it's 5 equals 2.
I need to change the change the coefficient to a 5 in front, and I now have 10 hydrogens. Okay. If we move through and look to the oxygens, how many oxygens on the left-hand side?
3 or 2.
We only have 2 on the left-hand side, and on the right-hand side,
3.
okay, 4 times 2 gets me 8 oxygens, plus 5 times 1 gets me 5, and I end up with 13. Okay. How do I make 2 equal to 13? Okay. I heard one person suggest decimals. Not a bad idea. Okay. Let's use 7.5. Okay. Did I do that right? I didn't do that right. 6.5. 6.5. Okay. If I did 6.5, 6.5 times 2 is 13. And that would count out my oxygens properly. But I now have half of an oxygen molecule. We're not allowed to have half a molecule. It's not possible-ish. Okay? So what we need to do is come up with some way to balance this. Ultimately, what this means is that somehow or another I've been set off incorrectly. Okay? How you go through and fix that is kind of up to you, and we'll work through 2 methods. One method, you screwed up, multiply everything by 2. Okay? Why pick 2? Why not 3 or 4 or 5? There's 2 oxygens. That's why we picked 2. It's O2. If that was O3, I'd need to pick 3. Okay? So if I go through and multiply everything by 2, how many CH4H10s would I have? 2. How many oxygens would I now have? Okay, so we'll come back to the 13 in a second. Because what we're doing is effectively resetting, saying something went wrong on this. Okay, and by resetting, that means I need to reset all of those all that work I just did. Yeah, I know that kind of sucked. Yes, I will show you a different method in a second. Oh! Okay. How many carbons on the left-hand side? On the right-hand side? 2. How do I make that 2 get me to a total of 8 carbons on the right-hand side? Change the coefficient to what? I have to make it 8. And I make it 8 by doing what? Multiplied by 4, right? Anybody remember what the coefficient was previously? 4. Interesting. If we look at our hydrogens, how many hydrogens do we have? On the left-hand side, we have 20. On the right-hand side, we have 4. How can I make that 4 into 20? I need to multiply it by 5. Okay. So to do that, my 2 becomes 10. What was the coefficient I had previously? Huh. Oxygen. How many oxygens do I have? Left-hand side. 4. Right-hand side? I've got 16 there, and I have 10 here. 8 times 2 is 16, right? Okay, just checking. And we've got 26. Okay. Now we run into a slight issue. How do I get the 4 up to 26? If that number becomes 13, what would I get? 26. I didn't have a coefficient there before because it didn't work right. Okay. If we go through and check, what happens? Everything's balanced now. All right. So what we went through and did is said, okay, we screwed up, change all of the coefficients through by 2, and now attempt to rebalance, and do whatever you got to do to rebalance. Okay. One of the things that was kind of suspicious that popped up is you noticed that for our carbon and our hydrogen, we ended up multiplying those through to get a new number by the previous coefficient. Okay. So I'm going to clear all that. I know everybody loves it when I do that. If we look at our previous work, we had what was it, 4, 5, and we had 6.5. I know we all love decimal points, and we all love fractions even more than we love decimal points. What is the fraction for 6.5, the smallest whole number fraction? 13/2. Remember I said we couldn't put 6.5 in there. This is 6.5, 13/2. But we said it's impossible to have a fraction, a part of a molecule. What did we end up doing to fix this? We multiplied our entire equation by 2. What is 1 times 2? What is 13.5 times 2? What is 4 times 2? What is 5 times 2? Okay. We can use that fractional value to help us predict what we have to multiply the equation by. Okay. Is that kind of a tricky concept to deal with? Yes. But it gets you there. Otherwise, you've got all sorts of weird stuff snowballing out of hell, and it becomes crazy. Right? These tend to be trickier to balance, right? Which is one of the reasons why you tend to not see them as much for balancing in 130. They definitely show up in 151 for balancing. Okay? What you should be able to do is recognize that this is combustion, and even further, recognize that this is going to be a little bit more challenging, potentially, to balance. Because sometimes when you look at a combustion reaction, you don't have to deal with these weird fraction things popping up on you. Sometimes it's just straightforward, you don't have to worry about it. Okay? But if it comes through and it doesn't balance nicely, you have to multiply by your denominator of the species that didn't work out. Okay? Yeah?
So if you see it's a combustion, can you just immediately multiply by the lowest subscript?
It doesn't always need to be multiplied.
Yeah.
So if you want to just immediately multiply by your elemental oxygen, sure, go through and do it. What happens if you go through and balance and we said it got 4, 26, 16, 20?
Reduce it.
Reduce it down to the smallest whole numbers. Okay? Because even if you multiplied by 2 and you didn't need to, then it's just one step higher, you can reduce it down lower. Okay? Last question I'll ask. Is this a redox reaction? How do we determine if it's a redox reaction? Something's being reduced, fair enough, yeah. Something's being oxidized, yeah. Officially, we'd have to go through and determine the oxidation numbers for every single element. It's a lot of work here. Is there a shortcut that we mentioned very quickly? The charge isn't going to be helpful here because there is no charge through it. That does not mean it's not redox. A lot of negatives in that, but that doesn't help us out necessarily.
What's on the product side?
What's that?
What the reaction produces?
No.
The Leo says GERD thing.
So it could be going through and determining the oxidation. And to do the Leo says GER, you have to know the oxidation numbers on the reactant side and the product side. Okay, that means going through and solving all of that work. Yes, that is perfectly valid. Okay, and that will get you to the correct answer. Is there a shortcut?
So oxygen has been combined with other elements, so we have oxygen compounds.
What is the oxidation number for anything in its elemental state? 0. If we look at our reactants, is there anything in its elemental state? Oxygen, all by itself. So its oxidation number is 0. If we take a look at oxygen in the product, it's now in a compound. As soon as oxygen becomes into a compound, its oxidation number becomes -2, which means it changed. Which means it's a redox reaction. I didn't ask if it was oxidized or reduced. I just said, is it a redox reaction? Yes, it is. You see something in its elemental state on one side of the equation, and it's not in its elemental state on the other side. That is, by definition, going to be a redox. Okay. It's a nice, quick shortcut that can help you look at an equation and say very quickly, that is a redox reaction. Okay. As was also suggested, you could look for charge. If the charge has changed, it absolutely is a redox reaction, an unbalanced redox reaction. Charge hasn't changed. That doesn't necessarily mean it's not redox. So you have to be careful with that terminology or that usage. What was the definition of oxidation? I know you're all going to give me the answer I would expect you to give, but what was the definition of oxidation? Loss of electrons, Leo, right? Okay, that looks at oxidation numbers. We said there was an alternate meaning for oxidation, on ultimately where oxidation was discovered and why we used the term oxidation. Kind of. Iron does get oxidized to rust. What happened to the iron when it rusts? It combines with oxygen. Right? If a species starts without oxygen and ends with oxygen, it was oxidized by definition. That's where our term oxidation came from. Take a look at the carbon on the reactant side. How many oxygens are bound to it? 0. How many oxygens are bound to carbon on the product side? 2. Did we increase the number of oxygens? Yep. By definition, we did an oxidation reaction to the carbon. Okay. It was oxidized. So there's lots of little tricks you can use to pick up and decide that this is indeed a redox reaction. Questions on that?
Does oxidation always have to deal with oxygen?
It does not always. Okay, so it's again one of those pseudo tricks because sometimes you will do a redox reaction that doesn't involve oxygen. So the original definition of oxidation really only worked because we saw it first in the presence of oxygen. And when we got rid of oxygen, oh, magically our boats don't rust anymore. Okay, well, yeah, there's no oxygen, so it's not going to do that reaction. But you can still do a redox reaction without oxygen. Yeah.
So since it's something that like occurs naturally, time is there like an exponential type of?
You want to be very careful bringing in time into the situation. We will talk briefly about time and its effects in chemistry very, very quickly at the end of the semester. Time is brought in an entire subject or an entire chapter in 152, second semester general chemistry. And it's usually the chapter that everybody freaks out at and does horribly with, okay? Because it is not a simple process. Other questions? Okay. So what we're going to do is cleanly move into 8 and 9. I kind of feel like those chapters should be mixed. 8 is kind of going through the general concept of this is what a mole is, use it. And then 9 says you just learned about equations and you learned about moles, put them together. Okay? To me, it makes sense to just do them all at once. Okay? There isn't really any necessary need to keep them separated. I will say one aspect of both 8 and 9 that is brought up that we will ignore within this section is references to volume. Okay. Any reference to volume in Chapter 8 and Chapter 9 you can ignore. If you've been going to the tutoring center for their, I always forget what it's called. What is it called? Workshop. If they're referencing volume, that's fine. You can listen to what they're saying. It is sort of useful to understand something about it, but the way it is presented is like a mole equals 22.4 liters. Okay? A mole equals 22.4 liters when we are at standard temperature, when we are at standard pressure, when we are a gas. Okay? So you would all be 6 feet tall when you stand on the appropriate height staircase. Why is that a useful measurement? Okay? That conversion is completely and utterly awful because you now start to correlate those two things to each other, and it's wrong. Okay? Only in very particular circumstances does it make sense to use. Okay? So I want to completely ignore that policy altogether. If you see it show up in questions in the back of the book, it's probably because you're doing questions I didn't ask you to do. Okay? So don't do those volume questions. There's just no need to talk about it as far as the context of moles go. Okay? Questions about that? Okay. So real quickly, spend a quick second, set up the work. What is the mass in micrograms of a 325 milligram aspirin tablet? I know you had to know how to do this, but we've done this conversion a couple times. So, how do we start all of our conversion problems? Okay, I'll accept that because you ran them all together. Officially, according to our textbook, we go with what we want as our answer on the extreme right. What do we want as our answer? Micrograms. What do we start with? 325 milligrams. Okay. Is milligram equal to microgram? No. So we have to do a conversion. So we'll set up a conversion. Ideally, what we would do is go milligram to microgram. Come on, there it goes. Do we have a direct conversion for those? No. So I can't directly convert across into micrograms. Do I know how to convert milligrams to something else? Grams. Okay. And this is where, going back to the powers of 10 thing, I've been really, really consistent on this process. If you've been talking to other people, you may be shifting around on it. So be careful with it. Milli means what? 10 to the negative 3. Your power of 10 will always show up in front of the base unit. Not top or bottom, the base unit. What is the base unit here? Milligram or gram? Gram. So my 10 to the negative 3 must show up in front of grams. What number then shows up in front of milligrams? 1. Is gram equal to microgram? No. Okay, so I need another conversion. Where should the gram conversion show up? On the bottom, because it needs to cancel the grams in the previous one. Where should my microgram show up, ideally? On top. Do I have a conversion between micrograms and grams?
Yes.
Yes. I know that micro equals 10 to the negative 6. My power of 10 always shows up in front of the base unit. The base unit in this case is grams, which is in the denominator. So I put my 10 to the negative 6 down here, and I put in front of micro 1. If I track my units, milligrams cancel, grams cancel, and my unit would be micrograms. I can now deal with entering this into the calculator, and I'd end up with my final answer. Questions?
Why can't you just multiply that 10 to the negative 3, 10 to the negative 3? That way.
That's exactly what we did.
Oh, okay.
Okay. The idea is to split out your conversion factors as best as possible. When we talked about this, where did we get this conversion factor? You had to memorize it. That is not how you spell memorize. Is it? I'm just going to do mem. I was right? Damn it. Hey, can I undo? Cool, there we go. Really?
Yeah.
Okay. I'll trust you. Where'd you get this conversion factor? Okay. That is given to you. You're not required to know it. You are required to use it. Okay. When we move into this next section, we're going to encounter a bunch more conversion factors. None of those conversion, actually I don't remember. I think none of those conversion factors I actually ask you to memorize. Okay. Avogadro's number, okay, which is the 6.022 times 10 to the negative 23rd, is written on the exam, I believe, on the front. So there's no conversion factor to memorize. Okay. But you have to find it. Where do you find it? On the front of the exam. There's a conversion factor between grams and moles. Where do we find that conversion factor? It's actually not on the front of the exam. It's on the periodic table, which is the second page of the exam. Okay? So what you're going to be responsible for doing is knowing where to find conversion factors. That is the trickiest part within this setup. The next tricky part with it, when we went through and did this conversion, we said milligram to microgram was our target. Oh, we didn't know how to do it. Did we know how to convert milligram to anything else? Yeah. How many other things do we know how to convert milligram into?
Tons.
One thing. Into grams. We have no other conversion factor. When you move into this chapter, you are going to be able to convert your number probably at least 3 different directions. Okay? So if you encounter this problem of, well, I don't know what to convert it to, guess. Did you get closer to your answer, or did you go somewhere that made no sense? If you went somewhere that made no sense, your guess was wrong. Guess again. Okay? That guessing process should be happening when? Now, on the homework, not on the exam. By going through and doing the wrong guesses now, you will learn what is wrong so that when you get to the exam, you will do it right. If what you're starting to do right now is look at the answer key or get someone to tell you what conversion factor to use, you're only used to seeing the answer correct. What happens when you get to the exam? There's nobody telling you what conversion factor to use, and you get the answer wrong. Okay. Struggle through using the wrong conversions. Fail now so that when you get to the exam, you don't fail. Okay? So, back to our Lego Hogwarts. How many Lego bricks went into this? We talked about this. We've got a lot of bricks. Okay? And I'm just going to pick some random number. We could list out something like this. Okay? That's a lot of bricks. Okay? And to say that to a group of people, we'd have to say 2, 0, 0, 0, 0, 0, 0, 0, 0. Okay? That's a lot of numbers to list out there. How could I shorten that down?
2 times 10 to the negative 6.
Cool. We could do 2 times 10 to the negative, or 10 to the 6, positive 6.
6, sorry. Positive 6.
The one I'm actually searching for is $2 million. No.
You gotta use a finger.
What happened to all the zeros? They turned into letters. They turned into a new unit. The mole, a new unit. Okay? The thing that's confusing about it is that it's not a power of 10 that we're getting out of million. It's this weird nebulous number that we have no concept of. Okay? That's fine. You don't need a concept of it. You just need to recognize what it is. It's just a new unit, okay, that represents a very large number. Okay? Chemistry is setting you up with a rule set. In fact, every class is setting you up with rule sets, allowing you to go through and process different things. Okay? What chemistry gives you the ability to do is how to build things. All things at a relatively tiny scale. What do formulas give you? Well, they tell us what atoms are necessary to build a molecule. So if I look at the formula of water, what does that formula tell me? I need hydrogen and oxygen. What else does it tell me? I need 2 hydrogens and 1 oxygen. Does it tell me anything about the mass of each of those? No. All it tells me is the individual amounts of them. Why? If it told you the mass, you'd then have to go weigh it to then react it. Wouldn't you rather just say, well, I've got 2 hydrogens and 1 oxygen, I put them together and there it is? Okay? It's a lot easier to just count the number of them. So that's what our formula gives us. An equation. What is the equation giving you? Well, pretty much the same thing. It's telling me how to build water. I need to take hydrogen, unfortunately diatomic hydrogen, and oxygen, unfortunately diatomic oxygen, and I will combine those to make water. Right? And I know to build that water I need 2 hydrogens and 1 oxygen. So I have an idea on what molecules I need to use to make that compound. That's all it's telling me. So how many hydrogens do I need to make water? How many elemental hydrogens do I need to make water? What is the elemental state of hydrogen? H2. How many H2s do I need to make water? 1. How many elemental oxygens do I need to make water?
2.
Okay, we're getting a lot of weird answers here. If you give me 1, I have left over 1 oxygen. We can't have leftover oxygen. What is the problem with interpreting this equation? It's not balanced. To use an equation properly, it must be a balanced equation. Hence, chapter 7. Right? So you have to be able to balance your equations. Once your equation is balanced, then you can interpret it. When we go through to balance this, what do we end up finding out? I will need 2 hydrogen molecules, and that will allow me to produce 2 water molecules. That's what the equation gives me. It gives me some of that useful information. Not only is that useful, I now have a way to convert hydrogen to water. If I give you 5, let's pick an easier number. Oh, it doesn't matter. 5 hydrogens. How much water could you possibly make? 5. How did I do that? If I gave you 5 hydrogens, how can I make water? Well, I wish there was a conversion factor that would allow me to convert hydrogen to water. What did the balance equation give me? For every 2 hydrogens, I have 2 waters. What happens when I multiply 5 times 2? I get 10. Divided by 2? 5. How many water molecules do I produce when I have 5 hydrogens? 5. The balanced equation gives me a conversion factor. Right out of the equation. That's what the equation means. Right? Incredibly useful. Okay. Let's go back to our number concept. Farmer has 72 chickens, and each chicken lays 2 eggs a day. How many eggs can the farmer collect per day? A lot. The farmer appreciates your accuracy.
144.
How do I convert 72 chickens into eggs? One chicken produces 2 eggs. How did you come up with that conversion factor? It says it in the problem. It's telling you. Each chicken lays 2 eggs. There's my conversion. So how do I know how many eggs he can get a day? Now, 2 times 72. 144. Okay. This farmer has a very particular issue. Cannot deal with numbers larger than 15. Actually, I'll be nicer. Can't deal with numbers larger than 20. And I apologize to farmers everywhere for this. Okay, I'm not saying that farmers can't count. Just, that's what I need for this question. Okay? Can't count higher than 20. Why would I pick a number like 20? Fingers and toes? Right? Okay. You gotta give me something to work with. Okay? Can only deal with the number 20. Okay? Or nothing larger than 20. You tell him 144 eggs, he's going to chase you off the property because he has no idea what you're talking about. Give him that number in such a way that he can now understand it. What are you suggesting?
12 dozen,
What is a dozen?
12 eggs.
Interesting. You can tell him that a dozen is 12 eggs. A dozen is less than 20. You can deal with that. As far as the number of eggs go, what do you then do? You are converting 144 eggs into what?
12 dozen.
Into dozens of eggs. How do you convert 144 eggs into dozens of eggs? Well, just giving me this divide by 12 crap. 1 dozen equals 12 eggs. You now tell him that he has 12 dozen eggs. He's perfectly happy. Okay. When we talk about moles, guess what a mole is? A dozen. It's the equivalent of a dozen. It's just a way to count the number of something. It just so happens that we can't count or comprehend the size of what a mole is. It's not as simple as just 12 eggs. It's 6.022 times 10 to the 23rd eggs. Okay? We can't deal with that number. We can't comprehend it. Okay? Yes, we picked an example on the farmer. We picked on the farmer. But you guys are in the exact same boat when it comes to a mole. You can't comprehend that number. So we convert it down into a different unit that we can now work with more manageably, where we don't have to deal with powers of 10. That is the point of a mole. For some reason, I think I have a bike on this. I'm not quite sure I have a bike on this. Why? So let's just skip that. So let's take a look at the equation concept and its quote-unquote weakness here. All right, this goes back to our conversions. Should I be asking this question about this equation, or can I answer the question about the equation shown? What do you mean, not yet?
How do we use moles in
Huh?
our, we haven't done moles a lot in class.
Wait, it actually has no reference to moles.
You gotta balance the equation first.
I can't make reference to how many molecules of CO2 are necessary because the equation isn't balanced. I don't have a way to convert between CO2 and sodium hydrogen carbonate because the equation isn't balanced. There is no direct conversion there because I haven't made it yet. I have to balance the equation first. How do I balance it? Oof. Minimally, I'd need a 2 there. Why? I need 2 sodiums. So what we'd go through and do is all of our rules. We have 2 on the left, 1 on the right. It needs to become 2. What do I do next? Okay. We could do carbonate as a piece. Not a bad idea. How many carbonates on the left do we have? How many CO3s do we have? 1. And on the right we have 2. Here's where we're going to run into an issue balancing carbonate, though. How many carbons do we have on the right now?
None.
Why none?
This is part of carbonate.
You just balanced it as part of carbonate. Can we balance carbonate? Yes, carbonate showed up the same on both sides of the equation. Unfortunately, we now have no way of balancing the carbon. That carbon from CO2 got folded into becoming a new carbonate. Okay, so we can't balance carbonate on its own. What we will have to do is balance out each of the elements. So, how many carbons on the left? That is 2. Wow. How many carbons on the right?
2.
How many hydrogens on the left?
2.
Hydrogens on the right? Fix that, sorry. How many oxygens on the left? 3, 4, 5, 6. Yeah, it's obnoxious when it shows up in a million different places. And on the right, 6. Is our equation balanced? Yeah. Now that we have the balanced equation, now we can answer the question that was asked. How many molecules of CO2 are necessary to make 2 molecules of sodium hydrogen carbonate? 1. Interesting. You did that conversion in your head. Stop doing it in your head. Write out the work. Okay. I want to make 2 molecules. Not to be confused with moles, I'm going to abbreviate molecules as MLCS of sodium hydrogen carbonate. And I want to make, or start with, solve for the molecules of CO2. What is the conversion factor between molecules of sodium hydrogen carbonate and molecules of CO2? For every 1 molecule of CO2, I get 2 molecules of sodium hydrogen carbonate. Where did those numbers come from? The balanced equation. What number shows up in front of CO2 in our equation? 1. What number shows up in front of sodium hydrogen carbonate in our equation? 2. This is why we balance equations. I now have a conversion factor between 2 different species. So as long as I'm in units of molecules or the number of a species, I can convert between substances. Now when I go through and use my equation, how many molecules of CO2 do I need? 1. 2 divided by 2 gets me 1. I now have my answer. I can change that number, that starting number of 2 molecules, into anything I want because I now have a conversion factor between those substances. Okay? Here's the trick. What is the mass of 2 molecules of CO2? How would we figure that out? Where do we have any information about mass of molecules? Periodic table. So we could pull out the periodic table. Okay? So we could look at our periodic table and we would look at, what did I say for CO2? Yeah.
You said 2, right?
Carbon and oxygen. Right? We got a lot of numbers for both carbon and oxygen for our CO2. For carbon, our atomic number is 6. Is that our mass?
No.
No. So we'll ignore our atomic number. We want to look at our atomic mass.
12.01.
Okay. So for carbon, it's 12.01. Okay. And if I want to figure out the atomic mass, I should add up, or the mass of my molecules, add up the mass of all those species. So carbon plus oxygen, which was 16.00, times 2. Why do I have to do it times 2? Or add another 16? There's 2 oxygens in the formula. We add this up, and what do we get? I want to say 40? 48.01. Way to get all specific on me. What's the question I'm now going to ask? What are the units? We are never allowed to come up with a number without any units. What are the units on 48.01? 16 times 2 is 32, plus 12.
It's 44 or what?
I was just listening to what you guys told me.
I had 88.02
44.
in my head.
What are the units? Atomic mass units. Okay. That is the mass for a single molecule of CO2. How do we know it's only a single molecule? Because we only took 1 carbon and 2 oxygens. That gives us our single molecule.
Double it.
Okay. So if we wanted to know the mass for 2 molecules,
Double it.
I'm going to argue you do not double it. That is the mass for 1 molecule,
Okay.
and I need 2 molecules. Okay. Effectively doubling it. Okay. What is the mass for an atomic mass unit? We go into the balance room. Our balance room, we put something on the scale and it goes, oh, that is 52 atomic mass units. What does the balance measure? Grams. So AMU, yes, our periodic table tells us that, but that's pretty useless because we go into our balance rooms, our labs, and it does not give us AMUs. What does it give us? Grams. What is the conversion factor between AMUs and grams? There is one. Unfortunately, I didn't put it on this slide, so I'm going to end up having to guess at it. 1 AMU, 1.614 times 10 to the negative 24th, I think, grams. Okay. That's a negative up there. So what is the mass of one molecule of CO2? A really, really tiny mass. We're looking at probably something on the order of 10 to the negative 23 grams. What did our balance measure to? 10 to the negative 3. We're off by, roughly a few orders of magnitude, like 20 orders of magnitude. Okay. We can't measure out 2 molecules of CO2. If I can't measure out 2 molecules of CO2, I can't actually even prove that all that work I did in the balancing of the equation is a valid system. Okay? That becomes a big, big problem because we can't support any of our work with experimental evidence. Okay? It turns out that not only does our periodic table report this in units of AMUs, it also reports it in something known as the molar mass, which happens to be the relationship between grams and moles. So for that same molecule, it is 44.01 grams in 1 mole of CO2. What do I now have? A conversion factor. This converts between the number of molecules and the mass. Incredibly helpful because now I can take my balanced equation and I can predict something about the numbers of molecules and I can convert that into a mass that I can then weigh out in the lab and verify that all the work I did balancing was actually true. Our mole concept allows us to tie these two disparate concepts to each other and allows us to verify that what we've been doing is valid and worthwhile. Without that mole concept, we have no experimental way of proving this information. All we've got is, well, yeah, it makes sense. Okay, I shouldn't be able to destroy matter. Well, why not? Because a chemist came through and developed the idea of a mole that we can now scientifically prove that this works. Okay. Oh, there it is. What did I say it was? I was darn close, wasn't I? I said 1 point. What did I say? 1.614. Well, there it is. It's 1.661 times 10 to the negative 24th grams equals 1 AMU. Okay. I was within a margin of error. So that gives us our AMUs. If I wanted to convert that into grams, we just did that. Okay. We start with what we want, and we write what we end with, and we just put together our conversion. Okay. Measuring that mass becomes incredibly difficult, so what we've done is invented this concept of a mole, because that scales it up big enough that we can now weigh it appropriately. Okay. Which is kind of an interesting concept. So this is what we end up putting out as our conversion. 1 mole is 6.022 times 10 to the 23rd atoms. Okay. Let's pick a really simple atom. Let's pick a hydrogen atom. Okay. Let's see if I'm doing this on the fly, so hopefully I do this right. If we pick a hydrogen atom, I want to know the mass per mole for a hydrogen atom. What do I know about the mass of a hydrogen atom? According to our periodic table, is 1.01 AMUs. So our AMU is this arbitrary mass unit, which is the mass per one atom. How do I set up my conversion here? Okay, AMU to grams. Good call. AMU is not grams, so I need to do a conversion. Where should AMU show up in my conversion? On the bottom. What should show up on top? Grams. That's our ideal situation. Do we have a conversion factor between those two? Dang it, and I got rid of it again. 1.661 times 10 to the minus 24th grams was 1 AMU. What are my units now? Grams per atom. Well, I want grams per mole for a hydrogen atom. Okay. So yes, I've got my grams, but I'm not there yet. I need to do another conversion. What's that other conversion need to be? I need to convert atoms into moles. Do we have a conversion factor that allows us to convert atoms to moles? Yeah, that's our Avogadro's number. What is that number? 6.022 times 10 to the 23rd atoms is 1 mole. Grams we don't want to cancel out. We want that in our answer. We want it in the numerator. If we do go through and cancel, we'll have atoms canceling, and my units would be grams per mole. A few of you got calculators out. Punch that into the calculator. What do we get? For those of you sitting without a calculator, think back to that a little bit earlier in the lecture. I actually told you what that answer was going to be already. My massive mathematical brain, I can pull the number out really quickly.
It's on the slide.
It is on the slide. What number do we get? Those of you punching in the calculator. I want it from a calculator. Calculator person has to tell me. I see 3 or 4 people with calculators. Pressure is on. And I see that you have a calculator in your hand, so I will now accept that answer as 1.01. Guess what? Avogadro's number is the inverse of our gram to AMU conversion. They cancel each other. Why? Because I need that many molecules to get up into a measurable mass amount. Avogadro, a long time ago, was able to figure this out and see that relationship. Okay. Did it with gases. Okay. Kind of a neat little observation. This means when we go through and do our calculations, typically what we'll end up using is our unit of grams, and we will convert between grams and moles. Why do we then ignore AMUs? Because AMUs is where everything started from. Why do we ignore it? What do you mean it's so small?
So tiny that we can't see it or measure it?
Not see it, or the last part, measure it. What is our unit for mass? Grams, not AMUs. So I have to get my mass unit into something that's workable and usable. So when we look at our periodic table, that atomic mass number will now be used as our molar mass. This gives us the ability to convert a mass of a substance over to the number of molecules. Once I know the number of molecules, what can I then do with it? I can use a balanced equation to convert that number of molecules into the number of molecules of product. Or how many molecules of the other reactant do I need to react with it? Okay. Which is referred to as stoichiometry. So the mole concept is really just a large number. Once I have the number, I've got in infinite different directions I can go. This is where doing your conversions becomes tricky, because as you go through and start to use, once you're in that mole unit, you can go 4 different directions. So picking what conversion factor to use becomes tricky once you're at that mole unit. Right? So let's do one. How many moles of aluminum are in 3.42 times 10 to the 21st atoms of aluminum? As with all conversions, what do we start with? What do we want? What do we want? When do we want it? Sorry. Moles of aluminum. Gotta keep something exciting. What did we start with? 3.42 atoms of aluminum. Okay. Are atoms the same thing as moles? No. So I need to do conversion. Atoms of aluminum on the bottom and moles of aluminum on top. I wish there was a conversion factor between atoms of aluminum and moles of aluminum. What is that conversion factor? .022 what? Times 10 to the 23rd what? Atoms of aluminum. So where does my 6.022 number show up? No, not the bottom. I think I heard somebody else say it. What was it?
Base
In no. Of atoms. Why does the 6.022 show up in front of atoms? Because in our conversion factor, where does the 6.022 show up? In front of atoms. It's not on the bottom, it's not on the top, it's in front of atoms. Very careful in that referencing. Remember we did this before where I yelled it out and said, kept putting it in front of, in front of. That's going to help you set up your conversions. Because that ties the number to the unit. Your unit solves the problem, not the numbers. As I spit all over my computer. Stop drinking water. What shows up in front of moles? 1. Why? That's what shows up in my conversion factor. Okay. What happens? Atoms of aluminum cancel, and I'd end up with the unit of moles of aluminum. I got to punch it into the calculator, and I get my answer. Okay. When you punch it into the calculator, or when you punch it into your calculator and you get an answer, if the answer you get is something like 5 times 10 to the 23rd moles of aluminum, what did you do? This is a hint. That's wrong. When you entered it into the calculator, you did 3.42 divided by 6.022 times 10 to the 23rd. According to the order of operations in your calculator, what you really did was 3.42 divided by 6.02. That quantity times 10 to the 23rd. That's not what you're trying to do. The 10 to the 23rd is where? In the denominator. Make sure you use parentheses or you do that calculation first. Okay? Be careful on entering that into your calculator.
So you need parentheses before the 6.02 tab. Just double parentheses.
So questions? Okay. Cool, I like this one. Nice layer up of difficulty. How many oxygen atoms are in 0.240 moles of oxygen? I'll give you a minute. And I apparently, for some reason, did not write out the question right on this last one. It's 3.42 times 10 to the 21st atoms of aluminum. So I'll write out our whole conversion. And it was 6.022 times 10 to the 23rd.
I got 5.68 times 10 to the 24.
Yeah, and that's because you left off that 10 to the 21st at the front. That was my fault. The work, I didn't show the work right.
Oh,
Was moles of aluminum. Make sure you use the full information from the question. So I, for some reason, did not include that times 10 to the 21st. Everybody see that mistake? Okay. You have to make sure you count the proper number. 3.42 is drastically different than 3.42 times 10 to the 21st. Okay. Like $3 versus 3 billion trillion zillion dollars. Kind of significant. Okay. So on this one's trickier. What do we want as our answer? We want oxygen atoms. What do we start with? 0.240 moles of oxygen. What do we do? What's that? Atoms on the bottom? Why would you put atoms on the bottom? Okay, so oxygen atoms on top and moles of oxygen on the bottom. Do we have a conversion between atoms and moles? Okay, yes, we have a conversion between moles and atoms when it's the same unit. Okay. How many dozen eggs are there in 53 oranges? Is that conversion valid? Okay, if there's a conversion factor. Can I use moles and atoms in this case? Why not? One is an oxygen atom and one is an oxygen molecule. Are those units the same? Nope, we'd be trying to convert oranges to eggs. Okay. The 6.022 cannot be used with these units. Okay. So what can we change about this to make sure that we use it properly? We can convert this to atoms of oxygen. Okay. 1 mole is 6.022 times 10 to the 23rd atoms of O2. Here's where, or technically molecules, but how do I convert atoms of O2 into atoms of O? Two atoms of oxygen are in one, quote unquote, atoms of O2. You have to use the formula to do your conversion. Okay. Questions on that? Okay. We are done for today.